Let's talk about the properties of the trapezoidal rule. There are three parts, A, B, C, A, B, and C. And let's start with A. If the function f is piecewise continuous, then the error converges to 0. What is piecewise continuous? Piecewise continuous means there might be jumps of the function, but on the integration interval there are only finite many. So if, for example, at most 8 jumps, but not infinite many. And if that is true, then it's guaranteed that the trapezoidal sum, this is SH, the trapezoidal sum corresponding to h, if that h gets small, then it's guaranteed that the correct value and the trapezoidal value are very close together. That's the least we can expect from a meaningful idea. Okay, let's continue with B. If f is 2 times continuous differentiable, what does that mean? That means something like that. No, here is an ink. This is not allowed if it's 2 times continuous differentiable. In this case, the first derivative would have a jump here. So this is not allowed. It has to continue like that. And if the function is of that type, then the convergence is fast. It converges like h squared. That means if that is h, then it looks like that. And compare that behavior to behavior like that. If you have this behavior, then you need to be very close to 0 to get a good approximation of the correct integral value, which we have here. But if convergence is like h squared, then this h would be a very good choice, and it's guaranteed that you are very close to the correct value. That's a big difference if convergence is present, or if convergence is present and convergence is quadratic. Now let's talk about C. If our function is periodic and we integrate, the integration interval is 1 period, so for example something like that, and then it continues here with a copy of that, okay, copy again and so on. If it's of that type and our integration interval is 1 period, then the trapezoidal rule is super convergent, and that means that instead of a 2 you can use a 3, you can use a 4, you can use a 5, you can use a 6, and it's always true that convergence is at least h to the power of 6 or 8 or 10, and that's unbelievable. That means that we are ultra flat here, ultra flat, and that means that it's not necessary to have a very small h. Small h's are enough to get very, very good approximations. So let's check that. Okay, I prepared some code. This is the code for our A part. We have a function, I named it trapezoidal function number 1, and this is this function. We will integrate our function from 0 to 3, and on the interval 0 to 1 we have the value 1, and outside of 0, 1 we have sign of exponential of x, and then we take the absolute value. I will show you the function. Let's run that code. And we will see the following. Here on that part we have constant 1, and outside of that we have sign of exponential of x, and that means it's a function between -1 and 1, and the absolute turns the values between 0 and 1. And here we have a kink, and here also, and here also, and here also, and here also. So in these points here, we are continuous, but we cannot differentiate and get a continuous answer. And here at this point 1, it's not continuous at all. So for this function, we are in the A situation, but not in the B situation. And what do we see? What are the trapezoidal values? If we are using 16 sections, then we get that answer, and that answer is far away from the correct integral value. And if we use 32 parts, then we get much closer to the correct value. If we're using 64 parts and so on, we are getting better and better, but we don't have this quadratic behavior. Okay, so we have only linear convergence. Then our second example, here we have the function sine of exponential of x, and there is no absolute value and there is no constant 1 function. Let's run that code. This is our function sine of exponential. Sine returns a value between 1 and -1, and the exponential of x instead of only x means that the frequency accelerates. Okay, but there is no kink and no jump, and then we are in the situation that we have a function which is 2 times continuously differentiable, and then we see this picture. This is the value for 16 parts. It's a little away from the correct value. This is the value for 32 parts and so on. And then we get this flat behavior. And that means having an h small here, then we get very, very good trapezoidal values. Here we see the same. This is the h and this is our value. And we see here with this h, 16, 32, 64, 100, 250, 512, 1000, 2000, 4000. If we have 4000 parts, then we are very close. We have 4 correct digits after the decimal point. And we have this quadratic behavior. Okay, and if we have a function which is infinite many often continuous differentiable, and if it's periodic and all that, this is the function exponential of sine x. We exchange the order. Exponential of sine x. Sine is a periodic function. 2 times pi later, it's the same value as it was before, and exponential of something periodic must be periodic again. Okay, if we use that function, then we see the following, and this is really, really fascinating. This is that function, exponential of sine of 0, we are here, exponential of sine of pi halved, we are here, and exponential of 3 times pi halved, we are here, and then this part, and then the function will continue exactly as it was before, and we are in the situation of being infinite many often differentiable. And then we see the following behavior, and this is really fascinating. Using one single part here, we started with 0 instead of the 4 above. Then our trapezoidal value is quite bad, and also with 2 parts it's quite bad, and 4 parts okay. And then we get a flat line, and that means the superconvergence. Here, this value is very, very close to the correct value, although we have only 1, 2, 4, 8 parts. So with very few evaluation points, we get very, very good results. Let's zoom in a little bit to see it better. Okay, it seems to be completely flat, and that means that the value on the right hand side is almost perfect. Here we can see that if we have one interval of length 2 pi, then this is our trapezoidal value, which is not very good. Having 2 parts, also a value which is not very good. And then for 8, we said with 8 we are almost perfect, and that's true. Let's check the 5th and the 6th digits after the decimal point. Let's run the code again. And then we see that this is our value for 8 parts, and this value is correct to the 5th digit after the decimal point. And if we use 16 parts, then we are almost done. We are correct until, yes, the last 2 digits may be not correct, but this is numerical rounding. Here we have some oscillations in these 2 digits, but that does not mean anything because that has to do with the nature of floating point numbers. Having 16 parts, we are more or less exact, and that's really, really fascinating. Okay, and this is that property. Normally, we are never in that situation, but in that situation, this is a really, really super surprising property, and so we have to mention it. Okay, these were the properties of the trapezoidal rule. And now let's talk about the implementation of the trapezoidal idea. We evaluate at linear spaced x values. Here the x values, here the evaluation process. And then the first value in octave arrays start with index 1 instead of index 0. And so we have 0.5 times y1 and 0.5 the last value, and all in between get weight 1, and then we have to sum all these values, and then we have to multiply with h. H is the difference of 2 succeeding x values, so we can subtract x2 minus x1. If we subtract x3 minus x2, that would be the same result, so let's subtract x2 minus x1. This is our h, and also possible would be b minus a divided by n. That would give us the same answer, and this is the trapezoidal value. Give me a function, give me the integration interval, and tell me how many parts you want, and then I return this value. What would be the strategy if we want to provide a function a user can use? And this function should be a little more comfortable, so the user maybe does not want to decide how many parts to use. And so the user normally says, okay, I want a result which is accurate at least as 1 divided by 1 million. The difference between the correct value and the value returned by the integration program should be less than 1 divided by 1 million. Then we start with 1 part, for example, and then we are calculating the trapezoidal sum. And then we double n, then we take n is equal to 2 parts, and then we are calculating the corresponding trapezoidal sum again. Then we can check what changed. If this change, if the difference of the 2 values is less than the tolerance, then we assume that further subdivisions, that means increasing n again, would have no effect to the result, and so we can return our value we calculated for n is 2. Normally this difference will be not small, because n is 1 and n is 2, it means very, very few evaluation points, so we double again. So then we will calculate the trapezoidal value for n is 4, and then we compare the 4 value and the n is 2 value. If the difference is less than 12, then we return the value. Otherwise, we calculate the sum for n is 8, and then we compare with the n is 4 value. And if this difference is small, okay, then we return the 8 value. Otherwise, we double. And so we double and double again until the value, the difference of the values is small. And that's the implementation here. The user gives us a function which we can evaluate. He gives us the integration interval and he gives us the desired tolerance. Then, as long as we have less than 1 million evaluation points We don't want to double infinite many often, so this is the restriction. As long as we are less than 1 million, then we calculate the trapezoidal value. Then we compare the new one to the old one. If the difference is less than tolerance, then we are done. We return this trapezoidal value and we return. Otherwise, we will double. That means remember the old trapezoidal value and double the evaluation points and then go into this loop again. And if we did not return here, then we reach that point and then we will return an error. So this is a very simple implementation, but I think the code, you can read the code and understand the code, and that is the idea. And here is our function called. Later we will develop new ideas, and then the only thing we have to do is exchange that call to some other call. Okay, this is our implementation. And then we will have what is close to a professional implementation. It's not really professional code, because for the sine function integrating from 0 to 2 pi we will get a problem, because the first trapezoidal value will be 0, the second one will be also 0, and that means that we return a 0. In this case this is the correct value, but it's a little alarming to be in that situation. So a professional implementation tries to avoid this situation, but it's not easy. We will later talk about that. So these were the remarks to the trapezoidal idea.